is Pedro.
Hello everyone, my name is Pedro Costa. I've become to know your favorite conference supporter, I believe, if I'm not mistaken. Sorry, I'm a little bit nervous. I never presented in such a big room with so many people, so my heart is under ultrasonic fatigue right now. So if I do speak or I do present something that you don't fully understand, you will feel free to ask me questions here or after the presentation. For the entire conference, you will find me running through the corridors. Feel free to ask. All right, so let's begin. Just the outline of the presentation. I'll be speaking in three different ultrasonic fatigue testing machines, all tested to the AISI P20 mild steel strength steel. Which is the simplest one: tension compression, pure torsion, and tension torsion, which Professor Manuel Freitas already spoke a little bit. I'll be speaking in more detail, but in not fully detail, because it's a lot of mechanical vibrations, which is not the main focus of this conference, but I feel free to ask any questions. This is one of my fields of research, is associated with mechanical vibrations, all right? Then we're going to talk about just a little bit of finite element analysis, but we'll focus more on experimental setup, and the fatigue results. All right. I will not talk about the advantages of ultrasonic fatigue. Some people already mentioned it. I will just do an introduction on the basis of it all. We use resonance as a way to achieve such high stresses at such high speed of 20,000 cycles per second. Okay, you use a piezoelectric transducer to excite a certain setup, which is carefully designed so that all mode shapes are cohesive between each other. We use normally a booster and a horn. Some people only use horns, and then we have an actual specimen. The horn and the booster main objective is to amplify the displacements coming from the piezoelectric transducer. The booster also has a support ring, and this is very important in all tests because the support ring is placed on the displacement node. This means where the mode shape does not have displacement, so you can hold it and the vibrations will not transport across the entire structure of the machine. All right, so all these main principles are transported to pure torsion, tension compression, and tension torsion. I know that here the details are not very fine, but the image will repeat in bigger scale, so you'll better understand it. So again, we use mode shape. In case of tension compression, we use longitudinal mode shapes with one displacement node in every single component. You can see, like in the greens, which is this is displacement, there is almost no displacement. This is where the support ring is placed, and this is where there's no displacement of the specimen, and where the stresses are highest. This is the fatigue testing region. Okay, coming and transporting this idea to the pure torsion, we built it based on a paper of Marine and Claude Bathias, which is one of the biggest names in ultrasonic fatigue. They use, again, the horn or the booster, if you may call it. This is just one that is excited with the actual displacement of the piezoelectric transducer. And there's a torsional horn, which is designed not to have resonance as a longitudinal, but in torsion. And they are connected transversely by a pin. And this is the way that we achieve pure torsion, because then the specimen is attached on the bottom, here on the bottom. And this specimen, again, is fully designed by finite element analysis, or in some cases in analytical calculations, to have 20,000 kilohertz, but in pure torsion. Okay, this is in bigger size. This is the specimen sliced just to see the behavior is having. Again, in the middle, there's a node displacement. He doesn't have torsion displacement, so the highest stress is in the center. Across all tests, you need to control the temperature. This is where high compressed air is coming from, and this is the temperature sensor, which we use across all three tests. Okay, tension compression, pure torsion, and tension torsion. Okay, now bringing to the most unique test of them all, tension torsion. Okay, we already spoke about this a little bit. The horn is special, but if you look at it just from afar without focusing a lot on details, this is tension compression very similar. The same booster, a similar horn, and the specimen kind of is the biggest difference here. The horn has slips, and these slips, what they make is transform the wave of longitudinal of vibration that is coming from the booster and transforms it into a combination of waves, the wave longitudinal and then transversal wave, which is torsion wave. This combination is then transported to the specimen, and then we have a rotation and an actual displacement provided to the specimen. When we have this, and I'm going to jump a little bit further and I'm going a little bit back, the specimen, to work, it needs to be excited in resonance in two mode shapes, in two natural frequencies simultaneously. This is the most complex part of the equipment. I will not talk about a lot how we can design it to have this working, but again, if you have any questions, I'll feel free to ask. But again, if we separate the modes, this is the longitudinal mode, very similar to the tension compression. It stretches and compresses, and there's the displacement in the center. Well, because the shear modulus is about 1/3, we do have 3 nodes at each throat, and this is what allows us to have 20,000 kilohertz at torsion mode. And thus we have a specimen that has the 2 modes with similar frequencies that can be excited simultaneously by the horn, which provides the 2 displacements at the same time. Okay, this is a visual in finite element analysis that provides, again, this is the longitudinal mode and this is the 3rd mode. There's a few points here that show you that this rotates in one direction, this on the opposite, again it is on the opposite. This is what allows the torsion to be provided. Now we tested this with AISI P20 metal, which is a mild strength metal with an OK harness. This is important because when you have this sort of mild strength steels, what you expect in very high cycle fatigue is surface initiation, not internal initiation. This is not the scope of this investigation, but if you see across the research, if you increase the harness and the strength of the steels, yes, you do get internal, but when you go down to less strength steels, mild steels, low strength steels, you begin to have surface failure and no failure at all. This is again dependent on the microstructure as well. Okay, so we expect surface and we get, I'm going to go back again, surface failure. Okay. The way that we measure all this is by a laser measurement and strain gauges. Okay, to measure rotation, we made some grooves and we transport this actual measurement of the rotation towards rotation, and then a few calculations we do get the stress. But anyway, we still place strain gauges, which are not very easy to place for such a small specimen, which is such a small strain gauge. Just to get clear, this is a very amplified image of the strain gauge, and we all do this by hand, only with a few marks to know exactly what the alignment is and how, where is the lowest area of the specimen. You need to have steady hands, and you should not drink coffee or smoke a cigarette before you do this, all right? Now, we always control the temperature of the specimens in all 3. We always use compressed air and fans to cool the entire system. We talked about in a few presentations of other people that the frequency changes. Yes, this changes because one thing, when we cool down the horn, there's heat coming up to the horn and the booster as well. So you're not only heating the specimen, you're heating the entire setup. If you heat the entire setup, the frequency of the entire setup will change, and thus you have change in frequency. This is not as simple to look at the frequency of the specimen. You need to look at the frequency of the entire setup. That's why you need to have a sort of background of vibrations to know exactly what you are working on. To measure the frequency of the setup is not to measure the frequency of the specimen. Okay? Now, when you have a fracture of the specimen, it doesn't fully fracture because the fracture nucleates, you lose rigidity, you lose frequency, the test comes to a stop. So it doesn't bring to failure in your machine. You need to go to another machine and fully break it. We have a ton of images with different specimens. These, I believe, are the most beautiful and easy to show. Just to look at the difference, this is a pure torsion specimen. It's a very small. This is again due to the shear modulus that is much lower than the Young modulus. Then to have this relationship between rigidity and mass, you need to have a much smaller specimen, while the tension torsion specimen fully occupies the machine. Okay. Now, as I've spoken before, you have surface failure. This, unless you have a defect that is really big. This was a case of only one specimen, and this is an inclusion, an aluminum oxide within the specimen. It was the only specimen that had interior crack initiation and failure. Afterwards, comparing to the pure torsion, we have a beginning a 0 degree initiation, but only in a fraction of space, followed by a around 45 degree propagation along the specimen. Now, combining the two, since we are analyzing tension and torsion, we get a weird mixture of the two behaviors, all right? That changes across different actual shear and actual ratios, okay? When you have a lot of shear, you can easily see that the degree of the specimen, this picture on the optical microscope is taken like this, so that it comes kind of on focus due to the plane of focus. And as you increase the shear, you increase the angle and get closer to 45 degrees, just as the pure torsion specimen, okay? So the first thing we did was to measure the crack initiation and angle. And we get something like this. This is a point a little bit out of scope, but what happens, something similar that Manuel Freitas has spoken, when you reach around the von Mises equivalent stress, you get closer and closer to 45 degrees, something that is closer and closer to the pure torsion specimen. Okay? Comparing specifically the 3 through SEM microscope, you do get a similar crack initiation to the tension compression specimen, and goes similar and more similar to the pure torsion when you get a higher and higher shear and axial stress. You do get also radial marks that increase in size as it propagates to the interior of the specimen, meaning that the specimen begins in mixed mode 1 and 2, more mode 1 in lower shear axial stress, more in mode 2 with higher shear and axial stress, and as it propagates to the interior, it begins to be more mode 2 propagation. As you can clearly see, very similar to the first images. There's a smooth black surface, almost close to the optical dark surface area in fish eye, then propagates to a smooth area, and then the radial marks kind of appear and grow in size in here, even with secondary cracks. All right. So in conclusion, the main objective of this test, to test so different shear and axial stresses, is to see that we can actually reach something that is close to the conventional way of tension torsion, to achieve different shear and axial stress, so that we can increase the research that we can apply in multi-axial fatigue within ultrasonic fatigue machines. And this is basically the gist of it all, that we actually were able to fully fracture a specimen in tension torsion, fully controlled throughout the entire time. All right, I think